So we've developed the Poisson distribution, had some sense for where it comes from. Let's now apply it. So we'll consider an example here in which we have many subintervals. We've divided up our axis into many subintervals, and we're told that the expected number of spikes in a trial is 10. So let's now ask, what is the probability of observing 5 spikes in a single trial? So the expected number is 10, but we can ask, what's the probability that instead of getting the expected number, we get something less than it? We get 5. And to answer that, we'll use the Poisson distribution. And what we need is two numbers. We need L, the expected number of spikes in a trial. And we're told that in the problem statement. 10 is the expected number of spikes. And then we also need to know N, the number of spikes observed. In this case, we observe 5. And we want to know what's the probability of observing 5 spikes when the expected number is 10. And we can just plug in these numbers to the Poisson distribution. And so we can do that. So we want to know the probability of 5 spikes. In this case, we just substitute in the values. Here, L is 10. We have this N is 5. And we could plug this into our calculators or MATLAB, and we get a number, 0.0378. So we expect about 3.7% of the time to get 5 spikes in a single trial, although the expected number is 10. Okay, so it's very easy to compute these quantities now that we have the Poisson distribution as one of our tools. We just need to remember what these values L and N represent. So let's now summarize our statistical model of some spiking. So this is a relatively simple model of spiking, and to start, what we did is we divided the time axis into many tiny subintervals. And then our model was a coin flip. And what we decided is that whether or not a spike occurs in each subinterval depends on our biased coin flip. So we flip our coin for each subinterval, and whenever we get an H, we say that a spike has occurred in that subinterval. We were then able to write down expressions for the probability of observing N spikes. So we want to know how many spikes do we observe in this single trial. And what is it? Well, when the M is small, we can use the binomial distribution, and we can compute the probability of getting N spikes in all of these subintervals, and we can compute this quantity. Or when M is large, we can use the Poisson distribution, where in this case we have an expected number of spikes that we think we'll get across this trial, and we ask what's the probability of not getting the expected number, but perhaps something different, N, another number of spikes. And the thing to note is that the binomial and Poisson distributions, they're the same in this case, but the Poisson distribution is more useful when we have a large M. So we may avoid computing things like M factorial in the binomial distribution, which might mess things up when M is very large. Instead, we can use the Poisson distribution. But they come from the same place. So those are the two distributions we eventually got to. And one thing to remember is some assumptions that went into this statistical model. And the most important assumption we make in this statistical model is that these coin flips are independent. So again, we divide up our time axis into lots of tiny subintervals, and we can ask a question: what happens in a particular subinterval? Well, we don't know whether or not a spike is going to occur there. We have to flip our coin and find out. And the important thing is that whatever happens in that subinterval is a coin flip, and it doesn't care at all about what happens in the previous subinterval. Each coin flip is independent. So the subinterval of interest here, it doesn't care at all what happened in the previous subinterval. And a question we can ask is whether or not this is a good model. So is this a good model of spiking? And the answer is sometimes. So sometimes it is a good model of spiking. And as we go along in this course, we'll think more about this notion of a refractory period, which means that after a neuron spikes, it needs to recharge for a certain amount of time before it can spike again. And it can't spike right away. And an illustrative example of this, which is also a rather crude example, is flushing a toilet. So you flush a toilet, and it takes some time for it to recharge before you can flush the toilet again. So here again is our spike train, or here again is our time axis, where we've divided up into tiny subintervals. And if we see a spike at a particular interval, what we would expect based on the biophysics of the neuron and knowing that it has this refractory period is that we will not observe a spike in the next subinterval. It takes some time for the neuron to recharge. So spiking in each subinterval is not really independent. But that's a primary assumption of our statistical model, is that each time bin is independent of the other. But we know based on biology that that's not the case. These subintervals are not independent. And it turns out when the neuron spikes rarely, maybe this doesn't matter so much. We don't have to worry about this refractory period, because we don't expect spikes to occur right one after the other very quickly if the spiking is rare. And we can also build much more complicated statistical models that try to take into account this history dependence. And if you're interested in that, you can take more math courses here at BU. And please feel free to email me or talk to me if you're interested in those. So what we'll do on Friday is we'll implement these things in MATLAB, and next week we'll start building biophysical models.